So today we're going to talk about the concept of mass and source terms of mass. If you remember, the Schwarzschild solution is a vacuum solution, which means that you don't have source terms, and this is usually a very practical way of confusing students because they ask the question, so how is it possible that you have curvature if you don't have mass? Because you don't have mass since we're in vacuum and you don't have source terms. So if you remember well, this is our universe, and in a finite time we can reach this r equals 2m, which leads us to the interior of a black hole. This is a future null infinity surface, and this is a past null infinity surface, and here we have a time-like infinity point in the future and the same in the past, and this is a space-like infinity point. Now, as I was explaining to you, within the black hole these are surfaces, slices if you want, of constant radii, which is why I was explaining that when you fall into a black hole, space-time around you will be very quickly changing. Depending on the mass of the black hole, the time that you need to reach the singularity will be this or that, but it will be a finite time, and it's not a very long time. So even if you have the impression that you're not moving, around you geometry will be changing very quickly. But the question is, where did this curvature come in the first place? Well, by drawing the line that I am drawing in dash now, we have assumed that the black hole has been there forever. Because of this point here. This is a time-like point in the past, right? A time-like point at infinity. So the question is, how is it possible if we are in vacuum? How is it possible that we have curvature if we don't have mass? Because we don't have mass. All of the mass that created this black hole in the first place has vanished. It has reached this singularity, and whatever it came from, it is not there anymore. So how is it possible that you have vacuum? So how is it possible that you have curvature if you don't have mass? And the truth is that this is a very usual misconception that I have seen in students and not students, also some people who call themselves physicists, which is the assumption that zero source terms necessarily imply the non-existence of sources. This is simply not true. And that's because sources are described not just by source terms, but also by boundary conditions. So, to see why this is so, let us, start with the simple example of calculating the electric field of a single point particle with an electric charge Q. Now, let's assume that this point particle is located at, for instance, x0. This is the location of the charge. Then the field equations are, as you know, this. Now, the boundary condition satisfied by the electric potential is derived from the following limit. This is the limit in which x, the radius, tends to infinity, plus infinity, more precisely, of the integral of s square of r, I will explain what this is, of E times d square x, which is exactly 4 pi q. Now, s square of r is a spherical surface of radius r, centered around the region x0, where we have our charge, okay? The sources here, in that sphere, cannot be described by source terms, because you have a finite charge compressed into a point, this one here. Now, a physicist would say that we can describe the charge of a point particle using a delta function. Now, this is true in a sense. A delta function, however, is not a function which maps a scalar to every point, but a function that maps other functions to a scalar. So the delta function is a function that we are mapping other functions to a scalar. Now, we refer to functions of this kind as distributions. In physics, or at least in physics literature, what we do is to translate an equation involving distributions, whose solutions would be themselves distributions, to regular equations involving simple functions. To give you an example of what I'm trying to convey here, we're going to explain, or we're going to see how this is done for the simple example that we mentioned earlier. We approximate the point charge with a family of smooth, spherically symmetric charge distributions, such that the integral rho epsilon at a given radius 4 pi r square dr is equals to q, and rho of epsilon of r is equals to 0 if r is larger than epsilon. And you see what we're doing here, right? Supposing that the solution E of epsilon exists, and it's like this, and the other one. Now, supposing that this solution exists, then Gauss' law tells us that the integral over that sphere of E of epsilon, this is supposed to be a vector, d square of x vector is equals to 4 pi q if r is larger than epsilon. Now, if we take the limit in which epsilon is tending to 0, the solution E to the original problem must satisfy the boundary condition. And what is that boundary condition? Well, the boundary condition is that the integral of the sphere around the charge of the electric field d square x is equals to 4 pi q. Furthermore, if we make the sensible assumption that the field vanishes at infinite distances, we get the boundary condition that we mentioned before. This one. This is what we get when we require that, or when we assume that the electric field vanishes at infinite distances. So, what we have shown, or at least tried to show, is that there are problems in which the sources for the field are described by 1, 0 source terms, and 2 non-trivial boundary conditions. I had to change the location because it was very loud at the balcony. In any case, so we could be very confident that you can always use delta functions to describe point-like sources instead of boundary conditions. But this is not always the case, and this is why I wanted to make a stress on what I was saying, because this is a misconception as well. In non-linear problems, it might not be possible to use a delta function due to in general technical difficulties related to the non-linearity of the problem we are dealing with. Such problems arise frequently in general relativity, which is what most interests us in this lecture, right? The simplest non-trivial solution is a Schwarzschild solution, which is a static spherically symmetric solution to the Einstein field equations. It is, in this sense, the exact analog of trying to describe the electric field of a point particle, and we discussed that in a previous lecture when I was making the comparison between the singularity and defining the electric field at the charge itself. When R is tending to 0, you have the electric field has a term which is 1 divided by 0, and then you have a problem. The source of the gravitational field is not described as a source term, but by symmetry conditions. In our case, the spherical symmetry, and staticity outside of the black hole, of course, as well as the boundary conditions that the metric reproduces Newton's law for gravity at very large distances. So you see, when we ask the question, why do we have a curvature if you don't have mass? You don't have mass, but you have boundary conditions, and those boundary conditions are responsible for the presence of curvature, as I have just explained to you for the classical case of the electric field.